The morning of March 11th, 1943, Kummersdorf Weapons Testing Ground, Brandenburg, Germany. Oberingenieur Klaus Fischer stood in the proving yard watching his test crew prepare an American M4A1 Sherman tank for endurance trials. The tank sat in the morning light, painted olive drab, the name War Daddy 2 still visible on its hull. Serial number WH058941. Captured from the First Armored Regiment at Sbeitla, Tunisia, 20 days earlier, transported by ship to Germany, delivered to the Army Weapons Office for evaluation. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Fischer was a mechanical engineer trained at the Technical University of Berlin. He had evaluated tank designs since 1939. He understood powertrains, transmissions, suspension systems. He knew what made a tank reliable, what made it fail. He had tested every German tank in service, Panzer Three, Panzer Four, Tiger, and now the Panther was entering production. He knew their strengths, documented their weaknesses, but the Sherman was different. This was an American tank, from a nation known for automobiles, not armor. The United States had entered tank design late, had limited experience with tracked vehicles, had never faced the engineering challenges Germany confronted on the Eastern Front. Yet here sat a Sherman, captured intact, ready for systematic evaluation. The testing protocol was straightforward. Run the tank through standard German acceptance trials, measure armor thickness, evaluate mobility, test the gun, examine the automotive components. Most critically, determine mechanical reliability. How long could the engine run before requiring overhaul? How durable was the transmission? How often did components fail? Fischer's team had prepared the Sherman carefully. They had checked the Continental R975 radial engine, a 9-cylinder air-cooled power plant producing 400 horsepower. Strange choice for a tank. The engine was designed for aircraft, adapted for ground use. The Germans used purpose-built tank engines, the Maybach HL 230 in the Panther, the Maybach HL 210 in the Panzer Four, engines designed from the beginning for armored vehicles. The American approach seemed improvised. Use what you have. An aircraft engine because no dedicated tank engine exists. Yet, the engine started immediately. Smooth idle, no unusual vibrations, temperature gauges normal, fuel consumption acceptable. Fischer walked around the Sherman. The hull was taller than German tanks, more upright. The turrets sat high, making the vehicle prominent. Poor tactical profile. Easy target. The armor was moderate. Frontal protection adequate against most German anti-tank guns at range. Side armor vulnerable. Nothing exceptional. The 7.5-centimeter gun was serviceable but unimpressive. Lower muzzle velocity than German guns. Adequate against light and medium armor, insufficient against heavier targets. On paper, the Sherman looked ordinary, not superior, not revolutionary. An adequate medium tank, nothing more. What German propaganda claimed about American industrial inferiority seemed confirmed. The Sherman was not a technological masterpiece, but Fischer was not examining propaganda claims. He was conducting engineering evaluation. And as the testing began, something became apparent that contradicted every assumption German engineers held about American tank design. The Sherman did not break. The endurance trial protocol required running tanks continuously to evaluate mechanical durability. Standard procedure for all German tanks: drive them until components failed, document the failures, calculate mean time between breakdowns. Every German tank tested at Kummersdorf had established failure patterns. The Panther's final drive failed early. Average lifespan approximately 150 kilometers according to field reports. The transmission stripped gears under stress. The engine overheated frequently, required constant maintenance. The Panzer Four was more reliable but still demanding. Suspension components wore quickly. Final drives needed replacement regularly. The engine required careful operation. Push it too hard and components failed. The Tiger was powerful but fragile. The Maybach HL230 engine was overstressed from its design specifications. Built for a 30-ton tank installed in a 57-ton vehicle, it struggled under the load. Transmission failures were common. Final drives lasted perhaps 800 kilometers before requiring overhaul. This was normal. This was expected. Complex machinery operating under extreme conditions failed regularly. German engineers designed around these limitations, planned for frequent maintenance, trained specialized crews to perform repairs, accepted that tanks would spend significant time disabled, awaiting parts, undergoing service. The Sherman changed this calculation. Fischer's team ran the Sherman for 50 hours, then 100 hours, then 200 hours. The Continental R975 kept running. No major failures, oil consumption was normal, engine temperature remained stable, the transmission functioned properly, all forward gears operational, reverse gear functional, steering responsive, tracks tensioned correctly, suspension performing adequately. The test crew reported minor issues, a leaking valve cover gasket, a worn track connector, normal wear items, nothing requiring engine removal, nothing demanding specialized tools, nothing that stopped the tank. At 250 hours of operation, Fischer assembled his evaluation team. They discussed the findings. The numbers were inescapable. The Sherman's engine had operated for 250 hours without major failure. The average German tank engine required overhaul or replacement well before this point. The Panther's Maybach HL230 averaged perhaps 150 hours in combat conditions before needing major service. The Panzer Four's Maybach HL120 managed slightly better, but still failed regularly. But here was an American tank using an improvised aircraft engine, operating reliably beyond German expectations. One of Fischer's colleagues, Hauptmann Werner Schulze from the weapons office, examined the engine compartment. The layout was different from German practice. The radial engine sat vertically, taking up significant space. The cooling system was simple, large air ducts, basic radiators. The design looked crude, unrefined. German engines used more sophisticated cooling, tighter packaging, more efficient layouts. Yet, the American engine ran cooler than German engines. The simple cooling system worked effectively. The large air ducts moved sufficient air. The basic radiators dissipated heat adequately. The design was not sophisticated, but it functioned reliably. Schulze pointed out the maintenance access. Engine panels opened easily. Large hatches provided clear access to components. Filters were accessible without disassembly. The oil dipstick was positioned for easy checking. The design prioritized maintainability. A crew with basic tools could service this engine in field conditions. German engines required more specialized access. The Panther's engine compartment was tightly packaged. Many components required partial disassembly to reach. Changing certain parts demanded factory-level equipment. The design optimized space efficiency at the cost of maintenance complexity. The Sherman sacrificed space for accessibility. The result was a taller tank, but an engine that field mechanics could service. Fischer examined the transmission. American design, Spicer synchromesh, 5 peak forward speeds, 1 reverse. The casing was positioned in the front hull, connected to the engine by a long drive shaft running through the fighting compartment. Unusual layout. German tanks typically placed the transmission near the engine to minimize driveshaft length. But the American transmission functioned smoothly. Gear shifts were positive. No grinding, no jumping out of gear, no stripped teeth. The clutch engaged properly. The brakes held effectively. After 250 hours, the transmission showed minimal wear. Fischer's report documented these findings. The Sherman's mechanical reliability exceeded German expectations significantly. The engine operated beyond the average lifespan of German tank engines. The transmission functioned without the failures common in German designs. The cooling system worked effectively despite its simplicity. Maintenance requirements were minimal compared to German tanks. But the report also noted limitations. The Sherman's armor protection was moderate. The gun was adequate but not exceptional. The height made it tactically vulnerable. The design emphasized reliability over performance. It was not a superweapon. It was a functional, dependable tank that worked consistently. What Fischer and his team discovered was a fundamental difference in design philosophy. German engineers pursued technical excellence, superior armor protection through extreme angles and thickness, more powerful guns with higher muzzle velocity, sophisticated suspension systems with overlapping road wheels, advanced optics with precise ranging, every system pushed to maximum capability. This approach created impressive specifications on paper. The Panther had excellent frontal armor. The gun could penetrate enemy tanks at extreme range. The optics allowed precise engagement. But the complexity made the design fragile. Overlapping road wheels complicated track maintenance. Advanced optics required careful adjustment. The powerful gun stressed the mounting systems. The angled armor required specialized manufacturing. Each sophisticated system added maintenance burden and failure points. The Americans pursued a different goal. They designed for mass production and field sustainability. The Sherman used simple, proven components, standardized parts, basic systems that worked reliably. The armor was adequate, not exceptional. The gun was sufficient, not superior. The suspension was conventional. The optics were functional. Nothing pushed beyond proven limits. This philosophy created a tank that performed acceptably in every category without excelling in any single area. But it also created a tank that worked day after day, week after week, with minimal maintenance, by crews with basic training, in conditions where specialized support was unavailable. Fischer's testing revealed this disparity in stark terms. The Sherman engine ran for hundreds of hours. German engines required overhaul after dozens, or perhaps 100 to 200 hours. The Sherman transmission functioned reliably. German transmissions failed regularly. The Sherman cooling system worked with simple components. German cooling systems demanded precise operation. The implications troubled Fischer. Germany was fighting a war of attrition. The Eastern Front consumed tanks at alarming rates, losses to combat, losses to mechanical failure, losses to lack of spare parts. German industrial capacity struggled to replace these losses. Production was limited. Quality was declining as alloy materials grew scarce. Experienced workers were conscripted into combat units. Meanwhile, American industrial capacity was growing. The Sherman was designed for mass production, multiple factories building identical components, standardized assembly processes, interchangeable parts across variants. The same turret fit on different hull types. The same final drive fit multiple models. This standardization enabled enormous production volumes. Fischer knew the production numbers. He had access to intelligence reports. American factories were producing thousands of Shermans monthly. Germany struggled to produce hundreds of Panthers. The disparity was overwhelming. And now his testing revealed that each American tank was more reliable than each German tank. The Americans were not just building more tanks, they were building better tanks from a reliability perspective, and tanks that required less maintenance, and tanks that stayed operational longer, and tanks that could be serviced by average crews with standard tools. The testing continued. Fischer's team ran the Sherman for 300 hours, still functional, minor wear items replaced, track pads worn, but not broken, engine seals leaking slightly, but not critically, transmission shifting normally, suspension performing adequately. At 300 hours, Fischer ordered a complete disassembly. Strip the engine, examine every component, measure wear patterns, document metallurgy, compare to German standards. The disassembly took 3 days. What the team found reinforced their conclusions. The engine components showed wear, but remained within tolerances. Piston rings had life remaining. Cylinder walls showed minimal scoring. The bearings had acceptable clearances. Valve stems were within specifications. The engine could have continued operating. The metallurgy was interesting. American steel was different from German steel, less refined in some ways, cruder manufacturing processes, but adequate material properties for the application. The Americans were not using advanced alloys. They were using standard industrial steel, available in large quantities, producible by existing mills, sufficient for the requirement. German metallurgy was more sophisticated, special alloys for high-stress components, advanced heat treatments for durability, precise manufacturing tolerances for optimal performance. But Germany faced alloy shortages, chrome, nickel, molybdenum, critical materials, increasingly unavailable. Factories substituted inferior materials. Quality declined. Components failed prematurely. The Americans used simpler materials, available abundantly. Their components were less technically advanced, but more consistently produced. This consistency enabled reliability. Every part met specifications because specifications matched available materials. Fischer wrote his final report in April 1943. The document was classified, distributed to weapons office staff, copies sent to the Panzer Commission, summary provided to senior Wehrmacht leadership. The report's conclusions were clear. The American Sherman tank demonstrated mechanical reliability superior to German tanks. Engine durability exceeded German tank engines significantly. Transmission reliability was notably better than German designs. Maintenance requirements were substantially lower. The design prioritized sustainability over peak performance. The report recommended studying American design philosophy. Consider simplification of German designs. Reduce complexity where possible. Prioritize reliability alongside performance. Accept moderate specifications if they enabled better field sustainability. These recommendations were largely ignored. The Panther continued production despite its mechanical problems. The Tiger II was approved for development despite being even more complex. German tank design continued pursuing technical superiority at the expense of reliability. Why were Fischer's findings dismissed? Several factors contributed. Political pressure demanded superior weapon systems. Propaganda claimed German technical excellence. Admitting American superiority contradicted official narratives. Additionally, German military doctrine emphasized quality over quantity. Superior individual tanks could compensate for numerical disadvantage, or so the theory claimed. But Fischer's report documented a fundamental problem with this theory. Quality without reliability meant tanks immobilized awaiting repairs. Numerical disadvantage worsened when your superior tanks broke down before reaching battle. The Panther's impressive specifications were irrelevant if the final drive failed after 150 kilometers. The Sherman's moderate specifications became advantageous because the tank kept functioning. A tank that worked was worth more than a tank with superior armor that sat disabled. Field reports from frontline units confirmed Fischer's findings. German tankers who used captured Shermans reported the reliability difference immediately. One Panzer commander whose unit operated captured Shermans in Italy noted in his after-action report that the American tanks required far less maintenance than German vehicles. They started reliably in cold weather. The engines did not overheat in summer. Track maintenance was straightforward. Crews with basic mechanical knowledge could keep them running. Meanwhile, German tanks demanded specialized attention. The Panther required experienced mechanics familiar with its complex systems. The overlapping road wheels froze solid in winter conditions. Mud packed between wheels, immobilizing the vehicle. Clearing frozen mud required hours of work with specialized tools. Sherman suspension was simpler. Conventional bogie wheels. Mud fell off easily. Ice could be knocked clear. The tank kept moving. These practical advantages multiplied across thousands of vehicles. American units maintained higher operational readiness. More tanks combat-ready at any given time. German units constantly struggled with maintenance backlogs. Tanks awaiting parts, tanks undergoing repair, tanks immobilized by failures that field mechanics could not fix. The French learned this lesson definitively after the war. France operated approximately 50 captured Panthers from 1945 through 1947. These tanks had been abandoned by German forces during the Normandy campaign. Many were relatively new vehicles, but French maintenance reports documented constant mechanical problems. The French War Ministry issued a comprehensive evaluation in 1947 titled Le Panther. The report was brutally honest. The Panther's weak point was its final drive, of too weak a design, with an average fatigue life of only 150 kilometers. The engine was unreliable, prone to overheating, with an average operational life of approximately 1,000 kilometers before requiring major overhaul. The transmission required careful operation to avoid failures. 150 kilometers before final drive replacement. This meant a Panther could barely move from its assembly plant to the front line before needing major repair. The distance from Paris to the German border is approximately 450 kilometers. A Panther would require 3 final drive replacements to make that journey. Compare this to the Sherman. American Army reports documented Sherman final drives lasting several thousand kilometers. The British tested Shermans in North Africa for over 2,000 kilometers without final drive failure. Soviet reports from Guards Tank Army indicated M4A2 Shermans averaged 2,000 to 2,500 kilometers between major overhauls. The disparity was absolute. The Sherman operated 5 to 10 times longer than the Panther between major repairs. This meant Sherman units could sustain operations while Panther units were constantly breaking down. Fischer understood these implications in March 1943. His Resort documented them clearly, but the Wehrmacht continued prioritizing technical sophistication over reliability. The result was catastrophic. By 1944, German panzer divisions were shadows of their authorized strength, not because of combat losses alone, because of mechanical failures that immobilized tanks faster than factories could produce replacements. American armored divisions, meanwhile, maintained high operational readiness throughout the war. The Sherman kept running. Supply systems kept them fueled, ammunition replenished, minor repairs completed. The logistics worked because the design enabled it. One German officer, captured after the Battle of the Bulge, made a telling observation during interrogation. He said American logistics reminded him of how a well-run civilian business would operate. Everything standardized, everything documented, everything planned. German logistics, he said, felt like permanent improvisation, constant emergency measures, never enough of anything in the right place at the right time. This difference emerged directly from design philosophy. The Sherman was designed to be supported. Standardized parts meant repair depots could stock components that fit multiple variants. Simple systems meant average mechanics could complete repairs. Reliable operation meant fewer repairs were needed. The Panther was designed for performance without adequate consideration for support. Complex systems required specialized expertise. Non-standard parts meant supply difficulties. Fragile components meant constant repairs. The design assumed support infrastructure that German logistics could not provide. Fischer's testing at Kummersdorf revealed this fundamental flaw in March 1943, over 2 years before Germany surrendered. The Wehrmacht had time to learn from American design philosophy, time to simplify designs, time to prioritize reliability. But institutional momentum, political pressure, and doctrinal assumptions prevented meaningful change. The Panther continued production with its fragile final drive. The Tiger II entered service despite being even more mechanically problematic. Resources flowed into technically sophisticated but operationally unreliable vehicles. Meanwhile, American factories continued producing Shermans, 50,000 units by war's end, each one capable of operating for hundreds of hours with basic maintenance, each one supported by a logistics system that kept them running. The production numbers tell part of the story. Germany built approximately 6,000 Panthers, the United States built approximately 50,000 Shermans, numerical superiority 8-1. But the reliability difference multiplied this advantage. If a Panther operated for 150 hours before requiring major repair and a Sherman operated for 250 hours, the Sherman provided 66% more operational time per vehicle. Apply this multiplier across 8 times as many vehicles, and the operational advantage becomes overwhelming. German forces faced not just numerically superior forces, but operationally superior forces. More enemy tanks, more often operational, more reliable in combat, better supported logistically. The combination was insurmountable. Fischer's report documented this reality in March 1943. War Daddy 2, serial number WH058941, captured at Sbeitla, transported to Kummersdorf, tested systematically. The engine ran beyond German expectations. The transmission functioned reliably. The cooling system worked effectively. The design prioritized what mattered: sustainability in field conditions. This was not German propaganda's image of American industrial inferiority. This was American industrial strength applied intelligently. Build adequate designs that work reliably, produce them in enormous quantities, support them effectively, accept moderate specifications if they enable better operational availability. The Wehrmacht learned this lesson through bitter experience. Every engagement with Sherman-equipped forces, every mechanically disabled Panther abandoned for lack of repair capacity, every supply crisis caused by complex logistics supporting fragile vehicles. By 1945, the lesson was undeniable. But by 1945, Germany had lost. The industrial war had been decided. American production had overwhelmed German capacity. American reliability had outlasted German sophistication. Fischer's testing had revealed this outcome 2 years before the defeat became obvious. War Daddy 2 had demonstrated in systematic trials what would be proven across thousands of battlefields. The Sherman was not a superior tank by German standards of armor protection or gun performance, but it was a superior weapon system by the standards that actually mattered: availability, reliability, supportability. The Americans had understood something German engineers missed. Winning a war requires weapons that work consistently, not weapons with impressive specifications. The Sherman worked day after day, battle after battle, with crews who had weeks of training rather than years, with mechanics using standard tools rather than specialized equipment, with logistics systems moving standardized parts rather than custom components. This was the revolution that Fischer's report documented, not a technological breakthrough, not a scientific advance, but a fundamental reimagining of what military hardware should be. Not the best possible design, but the best practical design. Not peak performance, but sustained performance. Not technical excellence, but operational effectiveness. War Daddy 2 had traveled from Tunisia to Germany, captured by Panzer Battalion 501, transported 350 kilometers to Tunis over 4.5 days, shipped across the Mediterranean, delivered to Kummersdorf, tested for 300 hours, disassembled, examined, documented. That single tank revealed the future of armored warfare: mass production of reliable designs, standardization enabling logistics, simplicity enabling field maintenance, adequacy enabling victory. The Wehrmacht did not embrace these lessons. Germany continued building sophisticated, fragile tanks until the factories were bombed into rubble. The Panther remained unreliable until the last unit surrendered. Technical excellence pursued to the end. Operational effectiveness sacrificed throughout. American factories continued producing Shermans until victory was achieved. Then production stopped. The need had been met. The war was won. The Sherman had done its job, not through superior armor, not through powerful guns, through reliability, through availability, through working when needed, where needed, consistently. The testing at Kummersdorf in March 1943 should have changed German tank production. It didn't. The reasons were complex, intertwined with politics, propaganda, and institutional momentum. But the consequences were straightforward. Germany continued building tanks that broke down, while America built tanks that kept running. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By summer 1943, the Panther was entering combat at Kursk, the largest tank battle in history, the ultimate test of German armor. Hitler had delayed Operation Citadel specifically to wait for Panthers. 200 units were rushed to the front. Brand new tanks with the latest technology, thick frontal armor, powerful 7.5 centimeter gun, advanced optics, everything German engineering could provide. On July 5, 1943, the first day of the offensive, only 40 Panthers remained operational by evening. The rest had broken down. Transmissions failed, final drives shattered, engines overheated and caught fire. Steering systems malfunctioned. Panthers were burning spontaneously without being hit by Soviet fire. Internal fires were destroying tanks that had never engaged enemy forces. General Heinz Guderian, Inspector General of Armored Troops, visited the front during the battle. He observed Panthers first-hand in combat conditions. His reports were damning. Final drives were failing catastrophically. Transmissions were breaking after minimal use. Engines were catching fire frequently. Guderian recommended halting Panther production until the fundamental problems could be resolved. His recommendation was ignored by higher command. Germany needed tanks desperately. The Eastern Front was consuming armored vehicles at an unsustainable rate. Production could not stop for engineering refinements. The approach was to make incremental improvements while continuing production and accepting high loss rates from mechanical failure. This was the opposite of what Fischer's testing had revealed. The Sherman succeeded because reliability was designed in from the beginning. The Panther failed because performance was prioritized over sustainability. Fixing the Panther required fundamental redesign, strengthening the final drive, enlarging transmission components, improving cooling systems, but such changes would delay production further, reduce output temporarily, create supply complications. So Germany continued building Panthers that broke down. Unit commanders learned to expect it. Maintenance companies became expert at field repairs. Recovery vehicles worked constantly retrieving disabled tanks. The system adapted to dysfunction instead of fixing the underlying problems. German field reports from Normandy in June 1944 documented the continuing failures. Panther engines typically lasted 1,400 to 1,500 kilometers before requiring major overhaul or replacement. But final drives failed much sooner, often after just a few hundred kilometers. Tank units constantly cannibalized disabled Panthers to keep others operational. The phrase used repeatedly in German reports was that Panthers had to be kept running through intensive maintenance, not that they ran reliably. This was the language of a fragile vehicle requiring constant attention. The Panther crew manual, published July 1st, 1944, included specific warnings about not overtaxing the steering system. The manual stated, "Also remember that it is not right and proper to torture the steering brake whenever one thinks it is necessary. This will break the engine quickly. Those who do this have no sense of tanks at all." This was not the language describing a reliable, well-engineered vehicle. This was the language describing a fragile vehicle that required careful handling to avoid catastrophic failure. Compare this to Sherman crew manuals. The instructions were straightforward. Start the engine, shift gears, drive. No warnings about coddling the transmission, no cautions about gentle steering. The Sherman was designed to be operated by average crews without extraordinary care. British tank crews who captured Panthers during the war and attempted to use them against German forces experienced these reliability problems directly. The most documented example was a Panther Ausführung G captured by the 4th Battalion Coldstream Guards in Holland in autumn 1944. The German crew had abandoned it during a retreat, claiming transmission faults. British tankers found it apparently intact, started the Maybach engine successfully, and decided to press it into service against its former owners. They named it Cuckoo, painted large white Allied recognition stars on the hull and turret to prevent friendly fire incidents, formed a crew from volunteers who learned to operate German controls. Cuckoo participated in several engagements over nearly 3 months. The crews reported that when the Panther worked, it was formidable. The 7.5 centimeter KWK-42 gun was powerful and accurate, far superior to guns mounted in Churchills. The optical sights, Zeiss-manufactured precision instruments, were superb, better than any British tank sights. The thick frontal armor provided confidence that German anti-tank guns could not penetrate it frontally, but Cuckoo required constant maintenance. The engine leaked oil continuously. Fuel consumption was enormous, far worse than British tanks operating in the same area. The steering needed frequent adjustment. The transmission, the component that had supposedly caused the German crew to abandon it initially, remained problematic throughout British service. It functioned, but it made concerning noises, grinding sounds during gear shifts, metallic clanking during hard maneuvering. British mechanics worked on Cuckoo constantly between operations, trying to keep it running. After nearly 3 months of use, mechanical failure ended Cuckoo's service. Historical sources differ on whether the final failure was fuel pump system or transmission components, but all agree mechanical breakdown, not enemy action, ended Britain's longest use of a captured Panther in combat operations. No spare parts were available to repair whatever had failed. German Panther components were not interchangeable with British parts. The supply chain for German equipment did not exist in Allied logistics. Cuckoo was withdrawn from service. The Coldstream Guards went back to using their Churchills and Cromwells, which were slower and less well-armed than the Panther, but vastly more reliable. A Churchill might not penetrate a Panther frontally, but a Churchill would still be running at the end of a week of continuous operations. The Panther would likely be broken down, waiting for parts and specialized maintenance. The French army had similar experiences after the war. France operated captured Panthers in the immediate post-war period, using them in French military units stationed in occupied Germany through the late 1940s. French maintenance reports documented constant mechanical problems, engine failures requiring replacement, transmission breakdowns, steering malfunctions, final drive failures. The French eventually abandoned captured Panthers because maintenance requirements were unsustainable. Despite having access to German spare parts stocks and German mechanics with Panther experience, the French could not keep these tanks operational reliably. By 1950, France had phased out captured German tanks entirely in favor of American-supplied Shermans and French-designed vehicles. On paper, the Panther was superior to both in firepower and armor protection. In practice, reliability determined operational value. A tank in the maintenance depot had zero combat value, regardless of its specifications. What emerged from all these experiences was a consistent pattern. The Panther tank was a maintenance-intensive, mechanically unreliable vehicle that required exceptional care and immediate access to spare parts to remain operational. In controlled conditions of a factory test program with skilled mechanics and full parts availability, a Panther could function adequately for limited periods. In actual combat conditions, with field maintenance, limited spare parts, and average crews under combat stress, Panthers broke down constantly. American forces, facing Panthers in combat, learned not to be intimidated by the tank's reputation. Yes, the Panther had thick frontal armor that was difficult to penetrate. Yes, it had a powerful gun that could destroy Allied tanks at long range. But it was mechanically fragile. Combat tactics evolved to exploit these mechanical weaknesses, force Panthers into situations requiring mechanical stress, make them maneuver in difficult terrain, make them climb hills, make them reverse rapidly, make them fight in close terrain where they could not use their range advantage. The Panther's mechanical weaknesses became tactical vulnerabilities that informed Allied combat doctrine. British tank tactics in Northwest Europe from summer 1944 onward specifically exploited Panther unreliability, forced the engagement into close terrain where Panthers could not use their superior gun range, keep them moving and maneuvering until something broke mechanically. A disabled Panther was just as combat ineffective as a destroyed Panther, and Panthers disabled themselves regularly without needing to be shot. German reports noted that many Panthers abandoned on the battlefield had no combat damage, only mechanical failures that crews could not repair in field conditions. The crews followed proper procedure. Attempt field repair. If repair is impossible, destroy critical components. Abandon the vehicle. Retreat on foot. The result was fields littered with Panthers, intact, except for deliberately damaged gun breeches and radios. Allied intelligence teams examined these abandoned Panthers. The findings confirmed Fischer's testing. Final drives failed frequently. Transmission gears stripped under load, engines overheated and seized, cooling systems leaked, fuel pumps failed. The problems were systemic, not isolated incidents. One British technical intelligence report from Normandy examined 12 abandoned Panthers in a single sector. 9 had mechanical failures as the primary cause of abandonment. Only 3 had been disabled by enemy fire. Of the 9 mechanical failures, 6 involved final drive or transmission problems. 2 had engine fires. 1 had steering system failure. The report concluded that the Panther was more likely to be disabled by its own mechanical problems than by Allied weapons. This assessment was shared with British tank units. The message was clear: engage Panthers aggressively. Their mechanical fragility was a greater weakness than Allied firepower disadvantage. Meanwhile, Sherman reliability enabled sustained operations that German forces could not match. American armored divisions maintained operational readiness rates above 70% throughout the Northwest Europe campaign. 70% of authorized tank strength combat ready at any given time. German panzer divisions struggled to maintain 50% readiness, often less. The disparity grew worse as the war progressed. Allied air superiority disrupted German logistics. Spare parts did not reach frontline units. Specialized maintenance equipment was destroyed in transit. Recovery vehicles were targeted by fighter bombers. The fragile German tanks became increasingly difficult to sustain. Sherman reliability partially compensated for Allied air power. Yes, air attacks destroyed German supply columns, but Sherman supply requirements were lower. The tanks needed less maintenance, fewer specialized parts. Standard tools sufficed for most repairs. Field mechanics could keep them running. By December 1944, during the Battle of the Bulge, the contrast was absolute. German forces launched their last major offensive in the West. The plan required capturing American fuel depots because German logistics could not supply adequate gasoline. The offensive depended on taking enemy supplies. This desperation revealed the fundamental logistical collapse. Germany could no longer sustain its own military operations, had to rely on capturing enemy resources. Meanwhile, American logistics functioned normally. Fuel depots were established, ammunition stocks were maintained, spare parts were available, the supply system worked. German tankers who captured American supply depots were astonished by the abundance. One panzer commander described entering a captured American depot and finding thousands of jerry cans of gasoline, crates of rations, boxes of spare parts, medical supplies, winter clothing, everything organized, everything labeled, everything abundant. He compared it to German supply situations: chronic shortages of everything, fuel rationed carefully, spare parts unavailable, food inadequate, medical supplies scarce. The contrast demonstrated industrial capacity differences more clearly than any battlefield engagement. The Battle of the Bulge consumed Germany's last strategic reserves without achieving strategic objectives. Kampfgruppe Piper. The spearhead unit advanced rapidly initially, but then ran out of fuel. Joachim Piper drove past 3 million gallons of American gasoline at Stavelot, 3 million gallons, 800 meters from his route, stacked in jerry cans along the roadside. He never saw it. He expected fuel depots to look like German depots. Storage tanks, buildings, infrastructure. The American depot was just fuel-stacked, waiting. No guards, no buildings, just supplies ready for distribution. Piper looked for the wrong thing and missed what he desperately needed. Without that fuel, his advance stopped. His Kampfgruppe was eventually surrounded and destroyed. Not by superior American tactics, by logistics failure. German tanks sat immobilized with empty fuel tanks. American tanks kept moving, kept fighting, kept their logistics supplied. The Bulge demonstrated that tactical excellence without logistical sustainability meant eventual defeat. German forces executed their initial attacks skillfully, achieved surprise, broke through American lines, advanced rapidly, but they could not sustain the advance. Fuel ran out. Ammunition was exhausted, spare parts were unavailable, mechanically disabled tanks were abandoned. American forces initially retreated, but then counterattacked. Their logistics kept functioning. Reinforcements arrived, supplies were delivered, damaged tanks were repaired or replaced. The system worked. Within weeks, German forces were pushed back to their starting positions. The offensive had failed. Germany's last reserves were destroyed. After the Ardennes, Germany could only retreat. No more offensives, no more strategic options, just delaying actions until the inevitable surrender. The Wehrmacht's mechanical mobility collapsed entirely. Tanks were abandoned en masse for lack of fuel. Recovery vehicles could not retrieve disabled tanks. Maintenance units could not repair broken components. Meanwhile, Allied forces advanced with functioning logistics. Sherman tanks rolled forward day after day. Breakdowns were repaired, fuel tanks were filled, ammunition was replenished. The contrast between functional and collapsed logistics was absolute. When Germany surrendered in May 1945, Wehrmacht soldiers were starving. Rations had collapsed completely. Supply systems had disintegrated. Many German prisoners of war gained weight in American captivity because they received regular meals for the first time in months. One German prisoner said, "When I was captured, I weighed 128 pounds. After 2 years as an American prisoner of war, I weighed 185. I'd gotten so fat you could no longer see my eyes." American prison camp rations were better than German combat rations. The logistical disparity had become absolute. America could feed its prisoners better than Germany could feed its soldiers. This outcome was visible in Fischer's testing in March 1943. War Daddy 2 demonstrated industrial capacity applied intelligently. The Sherman was not technically superior to German tanks by measures of armor or firepower, but it was operationally superior by measures that actually determined outcomes: reliability, maintainability, supportability. Germany never learned this lesson. The Wehrmacht continued pursuing technical excellence until the factories were destroyed. The Panther remained unreliable until the last unit surrendered. The final Panther, produced in March 1945, had the same fundamental final drive weakness as the first Panther tested at Kursk in July 1943. 2 years of production, no solution to the critical failure mode. American production, meanwhile, had refined the Sherman continuously. The M4A3 variant with the Ford GAA V8 engine became the preferred model, more reliable than the radial engine versions, better fuel economy, easier maintenance. The 7.6-centimeter gun variant provided improved anti-armor capability. Wet ammunition storage reduced fire risk. These were incremental improvements to an already reliable design, not revolutionary changes, just continuous refinement, better components, improved manufacturing, enhanced safety. Each change made the Sherman more effective without compromising its fundamental reliability. By war's end, the Sherman had evolved into a mature design, proven in combat, supported effectively, reliable in service, not the most heavily armored tank, not the most powerful gun, but a complete weapon system that worked. That was enough. That was victory. Fischer's report had documented this reality in March 1943. The implications were clear then. The consequences unfolded over the following 2 years. Germany lost the industrial war, lost the logistical war, lost the reliability war. Tactical skill could not compensate for systemic failures. The Sherman represented American industrial strength applied to military requirements, mass production of adequate designs, standardization enabling logistics, reliability enabling sustained operations. This was not glamorous, not technically impressive, but overwhelmingly effective. German tank design represented different priorities: technical sophistication, superior individual performance, emphasis on quality over quantity. These priorities created impressive machines that looked formidable in propaganda films, but they created weapons that broke down in actual service. The choice between these philosophies determined outcomes. Germany built 6,000 Panthers. America built 50,000 Shermans. Germany's Panthers averaged 150 kilometers per final drive. America's Shermans averaged several thousand kilometers between major overhauls. Multiply the production advantage by the reliability advantage. The operational disparity becomes insurmountable. This was the lesson Fischer's testing revealed. War Daddy 2 proved that American industrial design, dismissed by German propaganda as inferior, was actually superior where it mattered. Not in peak specifications, in sustained performance, not in technical elegance, in practical effectiveness. The Wehrmacht learned this through defeat. By 1945, the lesson was undeniable. But by 1945, learning was irrelevant. The war was lost. The outcome was determined. German tank design had failed not through lack of technical skill, but through misunderstanding what military hardware needed to accomplish. Fischer understood in March 1943. His report documented it clearly. But institutional momentum, political pressure, doctrinal assumptions prevented change. Germany continued building sophisticated, fragile tanks. America continued building simple, reliable tanks. The results were predictable, inevitable, decisive. War Daddy 2, serial number WH058941, captured at Sbeitla, tested at Kummersdorf, 300 hours of operation, minimal failures, superior reliability. The evidence was documented, the implications were clear, the lessons were ignored. That single Sherman revealed the future of armored warfare: mass production, standardization, reliability, adequacy enabling victory, not through superior armor, not through powerful guns, through working consistently, day after day, battle after battle, until the war was won. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.